Hey everyone, welcome back. This is lesson 3B, and in this lesson, we're going to continue talking about the randomized complete block design. In terms of notation, statistical model, we're going to introduce an idea of additivity, the hypothesis for an RCBD, and the ANOVA table. Hopefully, throughout as we continue through the course, you'll just start to notice that we're just expanding the statistical model and what effects are going into it, and that the ANOVA table stands regardless of your design, like a CRD, RCBD. Next week, we'll be talking about a generalized random complete block design. And so all we're doing is just extending the models to have more terms. And our goal of the class is to test if we have a difference in the treatment. Okay, so let's get started with this week and talk about some characteristics and parameters and go through the randomized complete block design. So first characteristic is our randomized complete block design will only have one treatment factor, one block factor, and we do a block wise randomization. Again, this goes back to our insecticide example where we were randomizing A, B, and C within each plot. Our parameters are little t for treatment and little b for block, where in each block we have t treatments. Okay, and this should make sense from lesson 3A, where we were saying that each treatment only appears in each block once. Our total number of experimental units will be B times T. And again, for a randomized complete block design, we only have one EU per treatment block combo. Foreshadow to next week, we will be able to have more. That's a foreshadow though. So now let's think about the data, how it's structured for a randomized complete block design. So we have our blocks 1 through B, and each treatment appears once in each block. So treatments are here. Now notice there is a block mean, which is in blue, and then we have our treatment means, which is in a pink, or at least it should be pink. And then we have our overall grand mean, which is in purple. Okay, we've talked about this dot bar notation before, so just kind of getting back used to that. So our statistical model for a randomized complete block design is here. And again, it's just an extension of our complete randomized design, or a CRD. And so we have our treatment effect here. We have our block effect. We have our grand mean. So again, in our RCD, we really only had mu, alpha, and epsilon. And now we're adding in this block term. And then we have our random error, where again, we're still assuming normality, it's centered at 0, and it has some type of variance. How we're gonna, our parameter estimation is seen here. Our grand mean, our treatment effect, or our treatment mean and our treatment effect, this should look familiar. Then we have our block mean and a block effect. And then we have a cell mean. And we'll talk a little bit more about this in like the upcoming notes. All of these estimates are also unbiased estimates. Okay, so now we're going to talk about a new term called additivity. So as we start talking about different types of ANOVA analysis, the idea of, we're going to start having this idea of non-additivity versus additivity. And so randomized complete block designs are additive designs. And so if we consider what our expected cell mean is, so again, here's our cell mean, what do we expect it to be? The expectation is going to be looking at the expectation of our Yij. So if we came back up to this model and took the expectation across, the expectation of mu is going to be mu. The expectation of alpha I is going to be alpha I. The expectation of beta j is going to be beta j. And the expectation of the error is going to come here, is 0. Expectation of our epsilon ij is equal to 0 because of this assumption. So if we took the expectation of that, which is our cell mean, we would have this. So what additivity is that if we were looking at the mu ij's in the same block, so the j's are the same, but differ by a treatment, then we'd only notice the treatment effect. So if we looked at the expected response within the same block, but they differed by treatment, then we'd get the treatment effect. Now, this one, if we looked at the expected response within the same treatment, i.e. I, but they differed by the block, the only difference is the block effect. So as we move from block to block, there can't be a difference among the treatment, is what this is saying. All right, so let's look at an interaction plot. So an interaction plot looks something like this. It's the plot of the estimated cell means. So first thing to notice is that these aren't the responses, they're the mu hats. Okay, this is also sometimes called a profile plot. I've rarely heard it called this, but I wanted to put that terminology in there just in case your research field does it. So let's look at the different parts of an interactive plot first. So we have our treatments down here. And then our blocks are associated through the color or the line. Okay, so here is our estimated cell mean for treatment A, block 2. Okay, that's how you just read it. And in RCBD, these will always be parallel. Parallel lines imply additivity, additivity implies parallel lines. Now, we will get to when there are non-parallel lines, which implies that it's non-additivity and we have a treatment block interaction. That will be later on. And so how this picture relates to what we were just talking about here is that if we were just saying, okay, if we look within the same block, let's say block 2, this green line, across treatments, this will differ by the treatment effect. So how much this differ is going to be the difference between these two treatments. Now, if we were looking in the same treatment, let's say these 3 in different blocks, then they're only going to differ by the block effect. So again, the treatment, how they relate to each other are the same. So treatment B is always higher than treatment A, regardless of the block. So treatment B, so in block 2, treatment B is always higher than A. In block 1, B is always higher than A. And in block 3, B is always higher than A. Okay. So if we go back to our insecticide example, push this up. With additivity of an randomized complete block design, we are unable to look at what's called a block treatment interaction. So again, if we have our rows maybe labeled A, B, C, and maybe over here it's B, A, C. Again, you would randomize those. If we have these row labels, we always say that plot 1 and 4, like the whole plot of 1 and the whole plot of 4, are going to differ for some reason, maybe shading, maybe it's this little goat eating and doing its weird goaty stuff. I don't know. But we're saying that these plots can differ. But the way that treatment A relates to treatment B in plot 1 is the same on how treatment A relates to treatment B in plot 4. So if A is higher than B in plot 1, we're assuming that A is also higher than B in plot 4. Okay? Now, if it happens that the treatments aren't related this way, we would need replications to help show this. And so that is, we would need a whole nother set of experimental units. Let's say plot 1 extends. We have a whole nother set of EUs where we're going to label A, C, B. These would be called replications, and we would need replication within this block to estimate the block treatment or treatment block interaction. This is foreshadowing to next week, okay? Since we don't have replication, no replication, and to be more specific, within block for RCBD. This is replication within block, what we're trying to show there. Since we don't have that, we assume parallel lines for this model. And it's not too crazy of an assumption. And okay, in relation to the insecticide problem, which would be this interaction plot, this is a plot generated that I generated in JUMP. I'll show you how to do it in JUMP and R if you watch those videos. We would say that the effect of the insecticide doesn't change, or the effect of the insecticide of how A relates to B does not change depending on your location. So if A is higher than B in one location, then A is higher than B in the second location or plot. And we see it, so it's basically a shift of the blocks. All right. Another thing to be very specific about is what is being plotted here. The interaction plot is plotting our estimated cell means. It is not plotting yi's. It is plotting maybe our mu hat 1, 1. Okay, so here this red one is treatment 1, block 2. So mu hat 2i. Okay, that is a key thing. I've seen that a lot from students where they'll plot the response and not the estimated cell mean. So I'm trying to help you guys not make that mistake, but sometimes we got to make mistakes to learn. So the interesting aspect, though, that I want to bring up with our mu maybe hat I j's, because again, this is what we're plotting in our interaction. The issue is that this cell that we're trying to estimate only has one data point. So there isn't really anything to average over. I mean, I guess you could average over 1 point, but it's still that 1 point, and it's not an average because an average requires summing and then dividing by a number. And so we don't have replicates. So to get this estimated cell mean, we need to take the overall block mean, and we take the overall treatment mean, and then we're going to subtract, so add, those are adding, and then we're going to subtract the overall. Okay, and so that's what we're seeing here for our estimated cell mean for 1, 1. So what are we estimating this on average to be, i.e. if we repeated this and collect, this experiment, what would we expect on average? We're taking the treatment mean for treatment 1, we're taking the treatment block, we're taking the block mean for block 1, and we're subtracting out the overall. Okay. Cool. So moving on, we're going to be, we have the partitions of the total sums of squares. Again, the total sums of squares is measuring the variability from all sources. And so we have our sums of square treatment. Here's the new part, sums of squares blocks. And then we have our sums of squares error. We have how they're all calculated if you were to do it by hand. Again, notice that our sums of squares treatment, this is doing the within, it's our alpha. It's measuring the variability due to the treatment. We have our sums of squares block, which is going to measure the variability due to the block. We have our sums of squared error. Okay. Now, just like with the completely randomized design, a CRD, our goal here is to test if there's a difference in the treatment mean. So in our insecticide example, do the 3 insecticides differ? And so a couple ways you can write your hypotheses are here. Personally, I really like these two better, where this is using the effect, this is using the means model. Sometimes these dots, I don't know why, not confuse me, but we'll get more dots. And so it could look a little cluttered. These two are pretty clean. Again, I'll accept any of these formulations. So again, our goal is to test, is there effect? What is the effect of the treatment? Is there an effect of the treatment, right? We're only incorporating block to block out variability. So let me say that one more time. The goal is what is the effect, or is there effect of the treatment? Block is incorporated only to block out variability, okay? So our test statistic is still the treatment signal to the noise. So it's still our SST divided by our degrees of freedom over our sums of squared error divided by the error degree of freedom. You can also look at it as SST over SSE. This is going to follow an F distribution with these degrees of freedom. Again, we'll reject our H naught or our null hypothesis and conclude that there's an effect if our p-value is less than alpha, or if we use an F table and we look at our F to observe greater than this F from the table. Okay, here's our ANOVA again, or our ANOVA table. Again, if I gave you some of these values, for a test or a homework, I would expect that you would understand the relationship and be able to fill out the whole table. So if I was to maybe get rid of SST and give you the degrees of freedom and the MST, I would expect that you can solve for the SST for tests and whatnot. As a test becomes closer, I'll make sure you guys understand exactly what you guys should be looking at. Notice we have a test statistic for the treatments, but not the blocks. This is because we do not test the blocks, and I'll talk more about that in the next lecture. Something I also want to make note of is in this ANOVA table, we have the word treatment and the word blocks. When you do software, or when you use software, it's not going to say treatment and it's not going to say blocks. It's going to end up saying, for our insecticide example, maybe insecticides and then plot. And so it's going to actually have the name. And when we go through our software video, I'll talk and show you guys what I mean for that. So that is the quick overview of a randomized complete block design. Now, to help us get a better understanding of it, let's go to some examples. Now, in your notes, I noticed that I put insecticide first, but quickly I want to do the highway paint example first, so we're just gonna flip. And then we'll come back to insecticide. So let's just do the highway paint example first. The reason I want to bring this one up first is because we talked about it in lesson 2, and I just kind of want to show the difference between a completely randomized design and a randomized complete block design. Okay. And then we'll get back to the insecticides. So Our original problem with the highway data from lesson 2, key lesson 2, was to compare reflectivity of 3 new paints to the one currently used. So we had 4 treatments and we had 16 similar highways, and we wanted to just randomly apply these 4 treatments to these 16 sections of highways. How we made this design was we labeled our EUs 1 through 16, so that's what I have here. Then we randomly applied 4 paints to these 16 EUs. So in R, what I did was I just took 1 through 16, shuffled them up, and then took the first 4, and we're going to say they're paint 1, took the next 4, they're paint 2, took the next 4, they're paint 3, took the next 4, paint 4. How you would do that in jump is you would just column shuffle. How you would do that in jump is you would write paint 1 4 times, paint 2 4 times, paint 3 4 times, paint 4 4 times, and then column shuffle. Okay? Now, this was from lesson 2. We are now going to add a new element of blocking. And so we now have this element that we have 4 different locations on a highway, and we want to apply the treatment. And so again, our T is 4, our little b is 4, and then we have 4 sections of paint within each block. So how our design is going to change is maybe we have some road in Florida, that could be block 1. We have some road in Virginia. We got some roads in California and New York. Okay, and so how we are going to randomly assign and design this is we're going to label, that should really be in like quotes, label our blocks. Again, typically blocks are already known in us. In this case, it's Florida, Virginia, Cali, and New York. And our insecticides, it was the plot. We're being very smart about how we block, because within block, we want everything homogeneous, and from block to block, it can be heterogeneous. So I'm also making the assumption that all the roads, these 4 sections in Florida, are homogeneous. Okay. Then within each block, we're going to label our EUs. So 1, 2, 3, 4, 1, 2, 3, 4. And then within each block, we're going to randomly assign the paints. So here's our blocks and here's our paints. And this is going to represent our EUs. So we can see that our block has all 4 treatments, all 4 treatments, all 4 treatments, and all 4 treatments. And so I just wanted to show you guys how the CRD design setup is different than the RCBD design. Okay, now let's get to the more interesting case of how do we do this analysis, what it looks like. So here's our data. We have our block means, our treatment means. We have our total sums of squared. We have our SST, our SSB, and then we use our additivity to get our SST and our F statistic. Again, on homework and exams, I don't expect you guys to do this by hand. Use software. Let's use the technology we have and be very modern, okay? So with this F statistic, I could go to a table and look at it that way, or again, we can just use software and we can get a p-value. Boom. Okay, and so since our p-value is less than our alpha of 0.05, we can reject the null and conclude that some of the 4 paints have significantly different percentage decrease in reflectivity. Okay, now before moving on to this statement, let's go back to our insecticide. So that was the highway example. I wanted to introduce that one first, just to show you how the 2 different designs are set up between a completely randomized and a randomized complete block. Okay, now let's go back to the insecticide real quick and go through that data. So we have researchers and they wanted to see the effect of 3 different insecticides. We have 4 lands, four plots of lands. and they're divided into 3 rows. So again, here's our data. And our hypotheses are that we want to see is there a difference? We have our ANOVA table. We get a p-value. And so since our p-value is less, you guys can't see that, awkward. P-value, and since our p-value is less than 0.05, we're going to reject the null and conclude that the insecticides have a difference on the seedling survival rate. Okay, now notice that both of our highway and insecticides resulted in showing us or telling us that there's an effect of the treatment. We can now do some supplementary analysis that we talked about with the complete randomized design, such as Fishers and Tukey's or some contrasts. And in your homework, you're going to have some problems that relate to this. If you watch your JUMP or R video, I will quickly go over it, but it will be very similar to what you saw in the CRD video. That's all I have. In our next lesson, we're going to be talking about air quotes testing with blocking, i.e. we're not supposed to test blocks, and I will go over why we shouldn't. Thank you very much and have a great day.